floor is yours. You have 10 minutes.
My title is Non-extendable rational Diophantine 3-tuples, compressing polynomials and special figurate numbers. Abstract of this paper: a rational Diophantine 3-tuple is a family of three non-zero rationals x, y, z with the property Dn such that xy plus n, yz plus n, xz plus n are perfect square. In this paper, a pair of rational polynomials and some special figurate numbers are utilized for their extension as triples and are proved to be non-extendable as quadruple. Introduction of this paper. The necessary literature survey that found as a way to write this paper is given as follows: a collection of x1, x2, etc. xm of m distinct non-zero rationals is called a rational Diophantine m tuple if xi xa plus 1 is a perfect square for all 1 less than or equal to I less than j less than or equal to m. The Greek mathematician Diophantine of Alexandria first analyzed the problem for searching four numbers such that the product of any two of them increased by unity is a perfect square. He spotted a set of four positive rationals 1 by 16, 33 by 16, 17 by 4, 1 by 16 with this property. Followed by Diophantine's, many mathematicians searched as triples or quadruples that can be extended to the next consecutive tuples. Recently, Gibbs found the first rational Diophantine sextuples are there. The Manuel Duello, Casaliki, and Mekij and Sikasai proved that there are infinitely many rational Diophantine sextuples. Through these legends, discover the Diophantine m tuples that are extendable. There are some cases where the rational Diophantine triples cannot be extended to the rational Diophantine quadruple. In this paper, we have focused on such a kind of numbers, say rational polynomials, polygonal numbers, central pyramidal numbers, and so on. We prove their non-extendability by showing that any two numbers of those quadruples does not meet the requirement of Diophantine m tuples for the particular property. To acquire keep knowledge in the Diophantine m tuples and the generalization, the readers are delivered to 7. This definition is main role played in this paper. A set of m non-zero rationals a1, a2, etc. am is called a regular Diophantine m tuple if ai aj plus q is a perfect square for all ij equal to 1 to etc. m. If the condition is not satisfied for any one pair of ai aj, then it is known as an irregular Diophantine m tuple. In this paper, we consider the three numbers. First one is rational numbers, and second one is polygonal numbers, and third one is pyramidal numbers. To check extendability of triples, and we can prove the theorem for irregular Diophantine quadruples. First problem: consider the two tuples RQ1, RQ2. 1 by 4w, 1 by n square w, satisfying the property d of n square w square plus 1. For all n greater than or equal to 3, to search for its extendability, let RQ be any other rational numbers with the same property. Here we see that one and 2, eliminating RQ3 between 1 and 2, we get equation 3, the choice of psi j plus RQ1h and omega equal to j plus RQ2h. Next. Substituting the equation 4 in equation 3, which is succeeding equation here. Next. For the choice of h is equal to 1, the values of j and psi are found to be j equal to 1 plus 2 n square w square divided by 2n w, psi equal to 4 n square w square plus n plus 2 divided by 4 n w. Next, ma'am. The values of psi can be employed to derive the rational number RQ3. Next, ma'am. Hence, RQ1, RQ2, RQ3 is a regular rational Diophantine triple with the property d of n square w square plus 1 for all n greater than or equal to 3. Next theorem, the RQ1. In this theorem, RQ1, RQ2, RQ3 satisfying the property, and RQ1 into RQ4 plus add a property, we get a rational numbers, not satisfying the definition. So this theorem RQ1, RQ2, RQ3, RQ4 is a irregular rational dependent quadruple. Next one. The corollary, the same RQ1, RQ2, RQ3, RQ4, but different the property d of n square w square minus 1. Again, this quadruples, so irregular rational dependent quadruples. Next one. So examples of irregular rational dependent quadruple. Next one. Problem 2. This problem, different rational numbers RQ5, RQ6. RQ5 1 by W1, RQ6 1 by 4 power N1 W. The first problem N1 is variable. Here first problem N is variable. Here N1 is a fixed number. And property D of 4 power N1 W1 square plus 2. Applying the same procedure, we obtain the regular rational dependent triple 1 by W1, 1 by 4 power N1 W1, 1 plus 2 power in the whole square plus 2 into 8 power N1 W1 the whole square divided by 4 N1 W1, satisfying property D of 4 N1 W1 square plus 2. RQ5, RQ6, RQ7, RQ8 here, then RQ5, RQ6, RQ7, RQ8 is a D of 4 power N1 W1 square plus 2, so irregular rational dependent quadruple. Since RQ5, RQ8 plus 4 power N1 W1 square plus 2 is not a perfect square, so the quadruple RQ5, RQ6, RQ7, RQ8 is a irregular rational dependent quadruple. The regular rational dependent triples and irregular rational dependent quadruples with respect to general formula for polygonal numbers. Consider the triples GPN1 and GPN2. The property D of n power 4 3 into 3w square minus 5w minus 1 plus n to 12w square minus 2 minus n squared 6w square minus 5w plus 1, so divided by 4. Certain whether it can be extended. Let GP3 be a rational number such that 7 and 8, eliminating GP3 between 7 and 8, we get a new equation. Eliminating G3, we get a equation. Consider theta and tau. Next one.
Sorry, ma'am. You have 2 minutes left. Please conclude and summarize your paper, please.
Okay. So theorem GP1, GP2, GP3, GP4 is a irregular rational dependent quadruple. Next ma'am. So examples of general polygonal. The third one is a central pyramidal number. We take a 2 central pyramidal number. One is center square pyramidal and center octal pyramidal number. So property minus 7 n power 6 plus 2 n square divided by 9 is a perfect square. Next ma'am. Here CPS, CPO, CPN, CPM is a irregular rational dependent quadruple with the property D of minus 7 n power 6 plus 2 n square divided by 9. The proof for all the combination of quadruples satisfying property except CPS into CPM plus add a property is a perfect square. Hence, say irregular rational dependent quadruple. Recent research focus on generation of dependent triples and quadruples from the dependent pair with a suitable property which involve polynomials. In this paper, we have come to the conclusion that not at all the rational dependent pairs and triples can be extended to rational dependent triples and quadruples respectively. Next, ma'am.